in and take a seat.
It's fun. Okay, it's good to hear. I thought a little you guys
Okay, everyone, we're going to get started.
I should go fun.
Right, we'll let everyone settle back in. Okay, so it's my pleasure to introduce Anowar Shajib, our last speaker for today. He'll be telling us he's from University of Chicago, and he'll be telling us his talk is on the at the intersection of astrophysics and cosmology, strong lensing by galaxies as a probe for the Hubble constant. Take it away.
Thanks a lot, Reina, for the nice introduction. So people can hear me? Okay. Okay. Is there like a knob or something? Or I can try to speak louder. What about people on the Zoom? Yeah. Yes, hello? How about now? Yeah.
So I think people on Zoom can hear you, but not in the room. It's not amplified in the room quite as much.
Okay. Is now better? Yeah. Okay, I can hear myself too. So, thanks a lot for inviting me. It's really an honor to be able to tell you about my research. So I'm an observational cosmologist that combines astrophysics of galaxies and elements of data science to resolve the biggest tension in the current cosmology, and I'm going to tell you about it. I'm going to tell you how my observational tool of choice, strong lensing, is going to give us an answer. I'm going to give you the current status of the measurement and then the roadmap for the next 10 years. So this is the third talk in a row about cosmology. So by now, even if you do not work in cosmology, you're all familiar with Lambda CDM model, etc. But let me just touch on the basic points that would be relevant for my talk. So in my opinion, the field of modern observational cosmology started a little less than 100 years ago when Edwin Hubble discovered that the universe is expanding. So that means that at a very early time of the universe, all the things in the universe was confined within a very tiny space, and then it started to expand very rapidly, the event we call as the Big Bang. And the universe has been expanding ever since. So the current expansion rate is called the Hubble constant. It's a constant in space, but it has been changing over time. But this constant, which is a constant of nature, is a central cosmological parameter. So it gives us the age of the universe directly. So that's one of the key cosmological questions that we can ask. And it also sets the distances to all the faraway galaxies. So over very many decades, through breakthroughs, through big discoveries, both on observational and theoretical grounds, now we have this standard model of cosmology called the Lambda CDM. You have seen this graph before, which is showing you the energy budget of the universe, 68% dark energy. That is the lambda in the Lambda CDM model. Then there is a big amount of matter in the dark matter, and our current paradigm is called collisionless particles. So that's the cold dark matter model, and only 5% of it is in the visible matter. So now this Lambda CDM model is remarkably successful, as Chang was telling us, in reproducing various kinds of observations. I think there's an echo right now. Okay, thank you. So let me just show you one example of how successful this Lambda CDM model is. So here is the map of the temperature fluctuation in the cosmic microwave background from the Planck satellite. So here's a little cartoon of the Planck satellite. Now, if we take the power spectra, we have seen similar power spectra in the previous talks. So this is basically showing you the scales of these fluctuations. And the point here is that the red dots are the data points, and the blue line is the model fit, only using 6 free parameters. So you can see like how well this simple 6-parameter model can reproduce or fit the data we have at the largest scale of the universe. Now, these temperature fluctuations or the CMB observation combined with the Lambda CDM model gives us a prediction for the current expansion rate, which is the Hubble constant. So these are the predicted values for the Hubble constant. So here you see the numbers with this unit. So this basically means a value of 70 kilometers per second per megaparsec means that the space with size of 1 megaparsec, which equals to roughly 3 million light years, is expanding at the rate of 70 kilometers per second. But this x-axis is showing you a timeline, and these predicted values from CMB plus Lambda CDM model is being refined over time as observations from WMAP satellite and then the Planck satellite were coming in. So these are the predicted values based on Lambda CDM model. So now as a physicist, let's go and measure this constant as another test for this Lambda CDM model. So to do that, one conventional method is to use a direct probe called the distance ladder. So the theme here of these direct measurements is to measure a distance. And because a cosmological distance has this inverse proportionality relation with the Hubble constant. So this is a distance ladder. It has multiple steps. In the first step, we use a geometric method called parallax to measure distances to a type of variable stars called Cepheids. And then that allows us to calibrate their absolute brightness. And then we can use these Cepheids as standard candles to go up to some nearby galaxies that are host of type 1a supernova. And then we calibrate the absolute brightness of type 1a supernova. And now when we have done it, now we can use this type 1a supernova as standard candles and go up to very far away galaxies and measure their distances. So that's how we can directly measure the Hubble constant. So what do we find? We find these gray data points coming from these Cepheid-based distance ladder measurements. And you see, shortly after the year 2000, there was a very good agreement between these two values. This is the Hubble Space Telescope's key project. But as the measurement became better and better, now you see there is a discrepancy arising. So this is called the Hubble tension. So to guide your eye, I will draw some line. And this is a 5 sigma difference. So this is very statistically significant. So this is not a tension only between just one CMB experiment and one method. So here is a snapshot of the landscape of the Hubble constant measurement coming from different types of probes. So here on this side, which I'm labeling as early universe, so this is another CMB experiment, the Atacama Cosmology Telescope, which Laura Newberg built. And then this is the data point that's coming from using baryonic acoustic oscillation as a probe of the Hubble constant from Sloan Digital Sky Survey. So these are, although this is looking at galaxy clustering statistics at a later time, the imprint in these statistics is still coming from the same CMB temperature fluctuation that we see in the early universe. So these imprints are based on early universe physics. So now on this side, these are direct measurement, just like the distance ladder. So some of these are different versions of the distance ladder. Instead of Cepheid stars, some other types of stars are being used to calibrate the first few rungs. So for example, TRGB, Myers, these are just different types of stars. So I'm not going into details like what those stars are, but the main point here is that you see a dichotomy arising. So the early universe physics-based prediction are all agreeing to this lower value of the Hubble constant, and the local direct measurement of the Hubble constant is giving you the higher value. So this is really intriguing because this 5 sigma difference, if it's not due to systematics in these measurements, that means that we are missing something in our Lambda CDM cosmology. So if it's not systematics, then it has to be some new physics. We need to extend our Lambda CDM cosmological model to be able to reconcile this difference. So there have been many theories in recent literature proposing how to resolve this tension. So one of the leading contender theory is a form of early dark energy that was in effect before the CMB photons started their free traveling toward us. So that's a very early phase of the universe. So to resolve this tension, we need to have an independent measurement at the 1% level. So it needs to be independent of these two ways to get to Hubble constant, so that it can tell us either presence of systematics, or it can confirm some new physics. So here I'm putting it as a goal, so that's where my talk is going. And you can see that the goal is 10 years from now at the year 2033. So another advantage of having an independent measurement that has 1% accuracy in the Hubble constant, that it will allow us to improve the precision on the dark energy parameter constraints that Chang and Elena was telling us about. So this is showing that if we have an independent prior on the Hubble constant, then it helps break some degeneracies in the parametric space. And then this will give us a 45% improvement on the joint constraint on dark energy parameter from stage 3 experiments, for example, dark energy survey. But for stage 4, it's a little less because things add up in quadrature, but still quite a good amount of improvement. So before I tell you how strong lensing is going to get there, so let me tell you why strong lensing. So the strong lensing measurement of the Hubble constant is a one-step measurement. So this is unlike the distance ladder. So it avoids risk of hidden systematics at various steps of the distance ladder. And then the physics is well understood. So strong lensing comes from the physics of general relativity. And this is not affected by dust. So lensing is achromatic. So in my talk from here on, I will tell you more about how we can use strong lensing to get to this point, to get to a 1% independent measurement of the Hubble constant. And out of the fully independent direct measurements of Hubble constant, strong lensing currently has the only type of measurement that has a clear pathway to get there. So first, I'm going to tell you about this measurement that we recently had, but then we found out some previously unaccounted source of uncertainty. So we redesigned our experiment and then led to this measurement with larger uncertainty. So this is at 8% current uncertainty. And then from there on, I'm going to tell you how we can get to a 2% intermediate goal at 4 years from now. And then after that, in 10 years, we'll get to 1%. So of course, you have some world experts in strong lensing. So some of you will need no introduction to strong lensing, but for the others, let me give you a very quick intuitive explanation like how strong lensing works. So you can see a fish swimming in an aquarium, and when it comes close to the corner of the aquarium, light is bending in such a way so you see two images of the same fish appearing. So we see similar phenomenon happening in space when we have a quasar at a very far away distance, and we have a galaxy in between us and the quasar. So light is bent by the gravitational effect of the intermediate galaxy, and then we see the background quasar to appear multiple times. So the image you just saw appearing at the corner, that was a real image of such a system, and you'll see more of these systems as I progress in the talk. So at this point, please allow me to take a quick commercial break for the experts in the audience. So strong lensing is useful for very many things. So one of them is to test dark matter models. So of course you have the world expert in testing dark matter models, Priya Natarajan, who uses strong lensing at the cluster scales to do that. But we can also use galaxy scale strong lensing, which is my focus, to do similar tests on dark matter models. So for example, to differentiate between the population statistics of substructure predicted by cold dark matter and warm dark matter models. And I know that Yale has a lot of activities on dark matter, both on theory and experimentation and space observations. And so there are work going on the dwarf galaxy scale, and also, as I mentioned, on the galaxy cluster scale. So my focus on the massive galaxy scale using strong lensing will nicely fit in and complete the whole mass range to probe dark matter models. So commercial break over, let's get back to my main story, which is to measure Hubble constant using strong lensing. So as I was showing you this video, when two photons started traveling from the background quasar, and they have traveled around different sides of the foreground galaxy, they will arrive at us with a time delay. And the time delay will happen because these two paths the photons have taken, they have different lengths. So there's a path distance. So this is a geometric contribution to the time delay. And these two photons will also go through different depths of the gravitational potential well. So that adds a gravitational delay, which is also called as the Shapiro delay. So we can measure this time delay. So here is an image of such a strongly lensed system. So you see 4 quasar images appearing. So I'm just taking image A and image B. And quasars are intrinsically variable, so their brightness fluctuates. So if we monitor their brightness over time, so we will find light curves like this, and we can see similar patterns appearing in these light curves with some delay. So for example, these two peaks. So that gives us the measurement of the time delay, which is delta T sub AV. Now, if you write down the formula for this time delay using general relativity, etc., then we see this main dependency on this measured time delay. So one dependence is this combination of angular diameter distances. So these are 3 cosmological distances. And in combination, they have this inverse proportionality relation to the Hubble constant. So this is where our information on Hubble constant comes from. But then we have these 2 contributing factors that makes up the time delay. So one is a geometric term, so which largely depends on where these images are appearing. We already see it in this image. And then there is this gravitational potential term, so which is causing the Shapiro delay. So now to get these or to estimate this potential term, what we do, we model the mass distribution in the lensing galaxy. And we do that using this kind of high resolution image. So this image is taken by the Hubble Space Telescope. You see a cartoon of the telescope here. And a simplistic model that we can take is a power law model, so which describes the radial mass density profile in these galaxies as a power law. And now you can ask, why such a simple model? Like, we know that these galaxies are made of dark matter and stars, and none of them are individually a power law. But it has been observed that the power law model usually works pretty well. So if we just take the total matter distribution as a simple power law, then it is sufficient to reproduce the stellar kinematics data, so which is the motions of the stars that traces the gravitational potential. And then it is sufficient to reproduce what we see in X-ray temperature profile coming from the hot gas in elliptical galaxies that is in hydrostatic equilibrium with the gravitational potential. And also in galaxy simulation that has baryonic effect implemented, there the mass profile is also approximately a power law. Now the keyword here is approximately. I'll come back to it a little later, but for now let's assume a pure power law model to describe the mass distribution. So how does it work in reproducing the imaging data we have of the lensing phenomenon? So here is a schematic showing you a very complicated lens system. Yeah, so this is a lens model that I did, and it's actually the most complicated lens model done ever. So we have this quasar at the very back. So we have these 4 images of this quasar. There is a second source galaxy in between the quasar and the central lens galaxy. And this source galaxy appears twice. And this source galaxy is not only a second source, it has its own lensing effect on the background quasar. And in our model, we had to take that into account to reproduce what we see in this imaging data. So there are multiple lens plane and multiple source plane. We ray trace through all these planes, but the lens mass model is a simple power law. And this power law model is still very capable of reproducing what we see in the observed image. And this is the residual as a proof of that. So now, assuming this power law model and using the observed time delay for this system, I measured the Hubble constant. So this is in the year 2020. But this is the 7th system that has been analyzed to measure the Hubble constant from. So this was done under the collaboration TD Cosmo, which is short for time delay cosmography. And before this 7th system, there were 6 more. So let me zoom in to this timeline here, so that we can see all the interesting things that is going to happen soon. So these are the previous 6 systems that were analyzed in the same way, assuming a power law mass model. And then in combination, this gives us this 2% measurement for these 7 systems. So this is a 2% measurement, agrees very nicely with the Cepheid-based local or direct measurement of the Hubble constant. Well, that just proves there is new physics, and because it proves there is no systematics in the Cepheid-based measurement, but not so fast. Why? Because of this code, so which says, in theory, there is no difference between theory and practice. In practice, there is. So this code is sometimes attributed to Einstein or Feynman or the baseball coach Yogi Berra. But what I found is that the earliest record in print for this code actually goes back to a Yale's philosophy student from the class of 1882. So a nice, interesting connection there. So the difference between theory and practice for an observer like me is systematics. So let me tell you how what is the major systematics in this kind of measurement using strong lensing. And this is probably going to be the most technical slide of my talk, so please bear with me. I'm going to give you a qualitative description of how this mass sheet transformation in lensing it can produce or some systematics in my measurement. So let's start with a power law model. So in a log-log plot of density versus radius, so this is a straight line. And as I said, this fits our imaging data very well. So now there is this mathematical transform called the mass sheet transformation, where we rescale the overall amplitude of the mass profile and then add an infinite sheet of constant mass. So that's where the mass sheet transformation name comes from. And after the transformation, the new mass profile will look something like this. And now the nature of this mathematical transformation is such that it leaves all the imaging observables invariant. So in other words, it will fit our imaging data equally well. But after the transformation, this is not a power law anymore. So the data allows these kind of mass profiles, but our model does not. Our model, if we just take a power law, it doesn't allow. So now, that means this power law mass model assumption that we have been taking implicitly breaks this mass sheet degeneracy. But this new mass profile will give us a new predicted potential difference because the mass profile shape changed. And then it would give us a new Hubble or a different Hubble constant. So that means if the true mass distribution in galaxies is not a power law and something like this, then the Hubble constant measured by us would be biased. So here, for a moment, let's forget about the context of this previous measurement. Only take a look at the lensing-based measurement of the Hubble constant and contrast that against the CMB plus lambda CDM prediction. So this is a 3 sigma difference. But because of the mass sheet degeneracy, if you take the gravitational lensing-based measurement as a fully independent measurement, then this difference at 3 sigma is a difference between 2 models. So one is the power law galaxy model, so which is a statement in astrophysics, and the Lambda CDM cosmological model. So the Lambda CDM cosmology has been tested very well, as I was telling at the very beginning in my talk. But the power law galaxy model hasn't been tested to the 1% accuracy that we want to have for our Hubble constant measurement. So for that reason, we have redesigned our experiment to allow mass models that have more freedom than the power law and allows the maximal degeneracy coming from the mass sheet transformation, and then constrain the shape of the mass profile using stellar kinematics, which also traces independently the gravitational potential. So once we did that, now the uncertainty became larger because of this more freedom in the mass model, and it now sits at 8% uncertainty from the 7 systems. So this is from the flexible mass model and stellar kinematics. But we want to get to 1%, and now we are at 8%. So how can we get there? So there are 2 ways we can have improvement in uncertainty. So one is using specially resolved velocity dispersion to have more information on the mass profile shapes, and also have some strong prior from a larger sample of galaxy lenses to tell us how mass profiles in elliptical galaxies, which are usually the central lensing galaxies, are. So first, specially resolved stellar kinematics. So just to give you an idea what I mean here, so usually we have a single aperture on the lensing galaxy. So this is an illustration of that. Then if we take the spectra, then we are only measuring the spectra coming from like just the integrate over this whole area of the aperture. But instead, we can use this awesome instrument at the Keck telescope, which many of you are also a user of. And there is this instrument called KCWI, which is an integral field unit. What it does is that it measures spectra at each of these pixels. So this is a 2D image representation of the whole data, but each of these pixels has a spectra measured using this instrument. So this yellow region is showing just where we measured the velocity dispersion or the stellar kinetics of the lensing galaxy. Looks like a Pac-Man for no particular reason. But these are just 2 example spectra that we have used to get the velocity dispersion of stars at different points on this galaxy. So the gray line is the data, the red line is the model fit. So you see, like, as we get close to the quasar here, these are the same systems, by the way. As this is HST image, this is Keck KCWA image. But like if you go close to the quasar, you see the quasar emission line is stronger, but far away from or at the center of the lensing galaxy, the emission line is not that strong. But what we use is these 2 absorption features, and the width of these absorption features tells us how fast stars are moving. So that's what we are using. Now, so we have measured the velocity dispersion at 41 different points within this region. And this specially resolved stellar kinematics gives us a much more precise information on the mass profile shape of the lensing galaxy. So for the experts in the audience, it also helps us breaking the mass ancestry degeneracy, which is like how the stellar orbits are aligned or like distributed between radial and tangential components. So now using all these like very powerful data only for one system, it gives us this 9% measurement of the Hubble constant. So to contrast that, so this is similar to what we got from 7 systems only using unresolved or the single aperture velocity dispersion. So this is just an illustration of how powerful this kind of data is for Hubble constant. So by the way, like I'm giving you a legend. So if you're like lost at any point of the talk, like which of these points came from what settings, etc., like you can take a quick look at this corner. So this is just the first system we have managed to get data for. This is a very challenging type of observation. So we have many more systems to get this kind of data for, but we are already working on getting data from Keck and JWST. We have a cycle 1 program approved, and we are proposing for more time. So the second way to gain precision is to use a prior from an external sample of galaxy lenses to have more information on the overall shape of the mass profile. So here is a sample of 23 galaxy lenses. So what I mean by galaxy lenses, if we zoom in to one of these systems and contrast it against one of the systems that I've shown you before. So in the galaxy lens, the background source galaxy doesn't have an active nucleus or which is a quasar. So we only see the arcs appearing. But if we have a quasar, then we also see the point images appearing. And for quasars, we can measure the time delay using their variability. But for galaxy lenses, we cannot. But we can still use their lensing information combined with their stellar kinematics to constrain how the overall mass profile is distributed in the lensing galaxy. So I have done that for this sample of 23 systems, combining stellar kinematics and weak lensing with the strong lensing information that we see in this imaging data. And Priya Natarajan is a world expert in combining all these different probes for the galaxy cluster lenses, but this is a similar way to look at the mass distribution for galaxy scale strong lensing systems. So here is an So here is an illustration of like the constrained mass profile. So individually in dark matter and stars, and the purple is the total matter distribution. And this is just for one lensing system. So for the experts in the audience, so weak lensing, so just for one single galaxy, the weak lensing information doesn't have a very high signal to noise ratio. So what is being done here is to use the weak lensing signal from a larger sample and staking them and using that as a prior on the halo mass-to-mass relation. So now if we look at how the total mass distribution deviates from a power law assumption from these 23 systems, then we find this. So this is showing you in percentage how much it deviates from a power law. So the 0 line would be no deviation from the power law. And what's important is how much the deviation is in this gray shaded region, because this is the radius where we see the images appearing or the arcs appearing. So this is the region where we want to get the shape of the mass profile right. So what these 23 galaxy lenses are telling us that the mass profile is consistent with the power law at 1 sigma, but still has a 5% difference. So now if you use these constraint as a prior on the mass profile shape of the 7 time delay systems, then we get this measurement. So now the first point is that the prior helps us in gaining precision. So now it has gone from 8% to 5%. But interestingly, now it sits right on top of the Planck value. So now the question is, is this prior justified to be used? Because when we use an external prior, we need to be sure that the selection between the samples being considered are identical. So now these two galaxy samples, they have 3 billion years of difference in age. So if there is significant evolution going on in between these two times, then we cannot use this prior. So that's still a question we are working to know the answer of. But in redshift terms, the time delay lenses have a mean redshift of 0.6. And the galaxy lenses that I've shown you just a couple slides before, they have a mean redshift of 0.2. So just to gather all the questions I've posed so far, and I'll give you the solutions to them. So is the parallel mass model accurate to 1%? Well, we do not know, but we can constrain the actual mass profile to 1% using more data. So one kind of data is using special results kinematics, and also to improve or gain precision on the Hubble constant, we can use an external mass profile prior. But to use the mass profile prior, we need to make sure if the prior is being appropriate. So, for that, we need to make sure that the samples that we are taking the prior from matches in selection with the time delay lenses. So, so from here on, this is the future part. So you see these points appearing after today. So you know these are not real data points; they're projection in the future. So to get to this 2% goal in about 4 years, we can get there using special results velocity dispersion from Keck telescope and the JWST. But to get to the ultimate goal of 1% precision, what we need that strong prior from a very large sample of galaxy lenses. And for that, the Vera Rubin Observatory and a Raman Space Telescope will be crucial to give us those large samples. So here is, I'm showing the current status of the data that we have in terms of having a sample of galaxy lenses that matches in age with the time delay lenses. So this is work done by my Chicago colleague, who is a graduate student, Chini Tan. So these are showing some lens modeling done with the current archival imaging of some of the lens systems that match in the age. So these are redshift 0.6 galaxies as the central lens. But one point you can notice is that data is noisy because they're short exposure. So this is a little challenging, but you can see Chini has done a remarkable job to produce very nice lens models. But this is just 3 examples. At this redshift for this age of galaxies, we have about 20 in total. But this is part of a larger project where we are modeling all the archival data for this kind of galaxy lenses. So, so to go from here, where we only have about 20 lens systems that match in the age or the selection function of the time delay lenses. So this is just a showing that the Sloan Digital Sky Survey gave us about 100 lens systems. So these are the systems that are discovered in the SDSS data. And then Dark Energy Survey gave us about 500 of these systems. So these circles represent the number. But now in the future, Rubin Observatory LSST will be giving us about 10,000 lens systems. So you see, this is a huge number of lens systems. So the first challenge is to find all these systems from this very huge size of data. So the conventional method to do that is to use machine learning. So this is the same finding a needle in the haystack problem that Peter Van Dokkum has when he's looking for low surface brightness galaxies from survey data. And so we can have synergistic approaches to devise these machine learning algorithms to find these lensing systems from the Rubin Observatory's data, and also with the Department of Statistics. So once we have found this data, the next thing we need to do is to model them. So that's where the science comes out of. So as a lens modeler, this is a time-consuming process for a human. And because that it involves a trial and error process and tweaking the model at multiple stages. So when I start a lens model, so I ask myself a few questions. So for example, how many images do I see? Are there additional source components or arcs? Or are there additional lensing objects? Because depending on the answers, that will give us the level of complexity that I need to account for in my lens model. But as you can see, these are all visual recognition tasks, which can be done using machine learning. So here is a proof of concept work done by a UCLA undergraduate student, Vedant Sahu, where we trained a neural network to tag each pixel in the image of a lensing system and tell us which component that pixel belongs to. So here, the yellow pixels, the neural network is telling us it belongs to the lens quasars. The blue pixels belong to the lens galaxy, and the purple are background pixels. So the machine learning or the machine has learned to recognize the lens components. So this will set up an artificial intelligence system that will model, or that will set up the lens model and then use traditional lens modeling softwares to optimize or find out the model parameters. So this is basically replacing the human modeler with artificial intelligence. So an analogy would be, this is ChatGPT for lens modeling. So before I finish my talk, so my next slide will be the summary slide. So let me stop for another commercial break. So as I told you, to get to 1% precision in the Hubble constant, we really need to know the mass profile shape in the lensing galaxies. But when we do that, we will also know how dark matter and stars are precisely distributed in these galaxies. And the shape of the dark matters have been shaped through like the formation and evolution processes of these galaxies. So these constraints on the profile shape also tells us about these different events that have shaped the dark matter halo. So by comparing what I observe from these lensing systems with galaxy simulations, we can know about the impact and timeline of the different baryonic feedback processes, and also the role of different types of mergers or their frequency in shaping these kind of massive galaxies. So of course, we have the author of the standard graduate textbook in this topic in the room, Frank van den Bosch. So my goal is to add or provide some new sections in that textbook in 10 years. So this is my summary slide. So the Hubble constant is a central cosmological parameter, but right now there is this 5 sigma tension between what the Lambda CDM model predicts from the CMB-based observation and what the direct measurement using Cepheid-calibrated ladder is giving us. So to resolve this tension, we need an independent measurement at the 1% precision and accuracy level. And my tool of choice is strong lensing, a time delays that will give us that in 10 years. And to get there, we really need a multi-probe and multidisciplinary approach. And current and next generation telescopes will be crucial to get us there. So before I finish, let me draw this analogy. So massive elliptical galaxies are the wise elderlies of the Galaxy Society. So they have had long lives filled up with stories of star formation and mergers. So if we really pay attention to them, to learn about those stories, and so they will tell us the solution to the biggest mystery in the current cosmology. Thank you.
Anowar.
So if this discrepancy turns out to be real, what do you think are the leading explanations right now?
Right. So so one thing is that the current problem, or the explanations or the proposed theories have, is that when we want to fix this tension, it breaks some other observation somewhere else. So for example, baryonic acoustic oscillation sets also gives us a very precise constraint on the Hubble constant times the sound horizon scale. So what this means is that we cannot just change Hubble constant by making some extension in the late universe. So when we change the Hubble constant, we also need to change the sound horizon scale in such a way so that it doesn't become inconsistent with the BAO observation. So that's why the leading contenders in terms of theory are all changes in the early universe. And the early dark energy has a way to make the sound horizon scale smaller. And so that will solve or that will be consistent in all three CMB, BAO, and the local measurements.
I was a bit confused about involving the weak lensing, the weak galaxy lensing. So am I correct that the idea is that you use a bunch of these systems, you stack them together, you try to get a constraint on the average power law slope or shape of the potential, and you use that as a prior in analyzing individual systems? Was that the idea?
No, so let me explain it a little more. So in that study, what we're doing is modeling the mass distribution in dark matter and stars individually. So the dark matter is some NOW profile with freedom for adiabatic contraction and expansion, and the stellar profile has freedom to account for some gradient in the mass ratio. So there is not assuming a power law, we are rather taking physical mass models. So now there we have these lack of information at the very large scale. So where so the overall normalization of the NFW halo is rather unconstrained if you only use stellar dynamics and strong lensing, because they only constrain the inner part. So now to have information on the overall normalization, we are using the strong weak lensing prior to so the prior is basically stellar mass to halo mass relation. So we have measured the stellar mass from the light of these galaxies, but then the prior then tells us what the overall amplitude of the halo mass should be.
Okay. So I'm nervous about that approach.
Okay.
For the reason that you stack galaxies that you ideally, you probably pick galaxies that have similar properties to the lens system that you're interested in.
Yeah.
And the hypothesis, they all live in similar halos. And therefore, again, my average is a good estimate of the halo of my system of interest. But we think we know that there's a fair amount of scatter. And that stack is a stack of halos of different shapes and masses and things. And it's not obvious that that best fit average halo mass is representative for your system in question. So have you thought about how you might want to go about trying to incorporate that in the analysis?
Right. So this comes back to this question of selection function. Like if we are really combining information from different types of galaxies in a self-consistent way. So right now, the number of galaxies, 23 systems, I do not think that's at the point where this bias from the selection function, when we're only looking at the sample of galaxy lenses, which is just 220 at this point. But when we'll have these very large samples from the upcoming surveys, there will have the statistical power to simultaneously account for the selection function. But that's an ongoing work. So we need to find out what are the best ways to mitigate the differences in the selection function. So that would be one of the pieces in my program. So using the LSST sample. So what are the selection differences between a general set of elliptic galaxies versus the lens systems?
I have a question on your use of the observing the stellar velocity dispersion to learn about the gravitational potential in the lensing galaxy. So I was intrigued by your observation of the stellar dispersion velocity field, which showed very large differences across the face of the galaxy. I think it was a 50% difference in dispersion going from one side of the galaxy to the other. That's a really huge difference in the outer part of a galaxy. So is that real? Say from going from the top to the bottom, the dispersion is very large difference. That's very unusual for a galaxy. So one question, is it real? And related to that, you need to be careful about just using a measure of dispersion to try to characterize the potential. You would want to know that the line shape is close to Gaussian, as opposed to having two distinct components at different velocities. Galaxies grow through mergers, and a lot of these galaxies, most of the stars are in one system, but then a few percent could be pieces of a merged galaxy, which locally is at a very different velocity from the others. So it's not a Gaussian shape at all. So you need to map out the full line of sight velocity distribution to relate the dispersion to the gravitational potential.
Right. Yeah. So these are very good points. So one thing here, I'm only showing the mean of the measurements. They have also uncertainties, which I'm not showing, and that the outer beams that you see there have large uncertainties, and those uncertainties also account for the systematics coming from, for example, some of the points that you have touched, that the shape of the Gaussian, etc. So what the information that goes into the measurement of the Hubble constant has all of these sources of systematic uncertainties in the velocity dispersion measurement accounted for. And for the shape of the lines here, so this is not at that high level of signal to noise ratio where we can see the deviations from Gaussian. So at this point, this is not a concern. There are other sources of systematics that has bigger contribution to the overall error bar than that.
Yeah.
Just wanted to ask you, I'm aware of another collaboration and does this stuff. Holy Cow, I think they call themselves. Yeah, Holy Cow. Could you comment on how your approach differs from theirs? And I think their latest results are approaching Planck. Is that right?
Right.
Comment,
So
please.
let me just make clear that the TD Cosmo collaboration that I mentioned, that is the current Holy Cow. So Holy Cow collaboration merged into TD Cosmo, because it also combined a few other collaborations. So this is like a larger umbrella collaboration. So all the measurements I'm showing you is actually also the previous 6 measurements that I've showed you in a few slides before. So 5 of them here are from the original Holy Cow. Mine was from this collaboration name, right? So these are just all branding and etc. But now all of these different brand names has merged into TD Cosmo. But what you mentioned that it's going to the Planck value is yeah, right. So yeah, so you mentioned this value. So this is when we use this external prior. Yeah.
Any other question? If not, let's thank the speaker again.
Thank you.
One more applause for all the speakers. All right, thank you. This concludes today's session for the Astrophysics Symposium. So there is lunch on the 3rd floor, and so please do join us there. Thank you.